This is chapter 1 for conceptual physics at Leaves of Learning School in Ohio. And what chapter 1 will cover, this follows very closely your textbook. We're going to talk about what science is, scientific measurements, mathematics, scientific methods, the scientific attitude, the relationship between science, art, and religion. We're going to talk about science and technology, a little compare and contrast, and how we can describe physics as being the basic science. What is science anyway? Well, we can talk about science as being a body of knowledge, what we know from people who've come before us, the conclusions that we've made, the consensus that people have reached. But it's also, most of the scientists I know will firmly believe that what we don't know is much greater than what we do know. So there is certainly more to learn, discover, observe, categorize. Um, Also, just because it's written down or published doesn't make it science. People have been exploring the world around them as long as there have been people. And it's really important to realize that even though our book shows a lot of men from Western Europe, it's not an old white man's adventure. Even those people had students, had family members, had people who worked for them that represented all kinds of people. And if you ever have a chance to study history, there's beautiful scientific discoveries in Asian cultures, in Arabic cultures. Um, we just happen to choose things that are written by people that are closer to our own culture. Let's move ahead to scientific measurements. If there's no measurements, it's not science. And we'll talk, in a couple chapters, we'll talk about Lord Kelvin. You might be familiar with measuring temperature in degrees Kelvin, and this is who established that. And read what Lord Kelvin has to say about measurements in science. And to restate that, he is saying that if we can't observe it, if we can't measure it, it might be well worth our thought, but it is certainly not science, and it's not something that other people can build on. So we're going to do an example on scientific measurements and how you can use simply the act of measuring and good logic to come to some scientific conclusions. So our measurements relate to what we know about something, and our example that we're going to use is a pinhole in a piece of cardboard to be able to calculate the diameter of the sun. And it all has to do with some simple math and some ratios. Uh, we will work through this in class. The pinhole works the same way that small holes in the leaves work, and what looks like it might just be dappled sunlight, in fact, is showing us images of the shape of the sun. And it's no more obvious than when there's an eclipse, as this woman is pointing out to us, that in the event of an eclipse, like in this picture, we will, in fact, see that crescent shape. We're going to talk about a fellow called Eratosthenes, who several hundred years BCE was able to make a very accurate measurement of the diameter of the Earth simply by observations. Now, just a heads up, this will not be anything on any test, um, but it's an interesting thing for you to be aware of. Let's look at another early scientific measurement, Aristarchus, and he is using his observations and what he could measure to calculate the distance and the size of the moon. All right, We're going to move ahead briefly to mathematics, which is the language of science. Now, as you continue with your education, and if you take another physics class at university, you'll probably do a calculus-based physics class. Ours is limited to algebra and geometry, so it's more conceptual. Mathematics is um, what happened 4 centuries ago is that Newton actually invented calculus so that he could infer and calculate from his observations of motion some mathematics that supported that. Uh, when we are using our mathematical terms, it doesn't matter your culture, your language, your background, your political opinion. When we are talking mathematical terms, when we're talking what we've measured, when we're talking calculations and ratios, the data stands alone and it is separate from the people who are expressing the ideas. And the data helps us describe the concepts that we see. Even though this is a conceptual physics class, we will have equations, we will have problems, it just won't include calculus. The equations are going to be how you remember your relationships and how you guide your thinking. Now, our next topic in the book is scientific method. I'm sure that you've had this several times. As a brief review with the scientific method, particularly as you continue your studies, you know, Mrs. So-and-so's from third grade scientific method may not be the one that everybody uses, but there are similarities. In general, we are systematic. We've got principles, we've got procedures. We work with the position, the formulation of a problem, and the most important part, we've got observation and data collection that comes through experimentation. These are experiments that you can repeat. These are experiments that other people can repeat. And we look for either the data being reproduced and replicable, or we look for what did we not anticipate in an experiment that caused the data to be different. From this, we form, we test, we validate a hypothesis. And the big thing to make it scientific is that it is repeatable. If you have an experiment or a few experiments that show you a conclusion, it may not be enough to get excited about unless you can repeat it and other people can repeat it. If it's not repeatable, then probably something was going on that we weren't aware of. The important thing is the repeatability. In general, we pose a question, we pose something that we're not aware of, and then we make an educated guess as to what's going to happen, and we predict what is going to happen. From that, we build an experiment to test the predictions, and we formalize some general rules that organizes this, kind of an if-then situation. So that was the scientific method. And now we're going to talk about the scientific attitude, which is a little bit different than what you might be used to. The scientific attitude is the idea that we're always asking, we're looking, we're searching. And in fact, in that circumstance, when we see data that is different than what we expected, we get really excited because that means that there's something that we don't know. The scientific attitude is one of experimentation. We actually want to test our hypothesis. We want to put our question to an experiment, to gathering some data. And when something happens that we don't expect, it either means that our experiment was in error or our hypothesis was in error, but what it mostly means is that there's something new to learn. We always want to see the data. A good scientist should be excited to see data that's different than what he or she anticipated. It means that there's something new to learn. It means that there's more complexity in the situation than what he or she first identified. Unless you can discount your experimental method, you must accept your experimental finding. And a good scientific attitude says that when I get data that I didn't expect, that means that I need to revise my theory. A good scientist will also challenge his or her own beliefs. You can have many, many reasons why you believe a certain thing, but when your data comes up against it, it should give you pause to really consider what it is you believed in the first place. And a good scientist will also understand the point of view of the people who are arguing the opposite point. It's almost like a debate that a good scientist will have the theories and the data from multiple sides of an issue and frame the debate around the data, not opinions. There are a couple terms, this is a clue, there are a couple terms that you will want to remember. And when we look at a fact, that means that it's not just some people, but many competent people have made similar observations about the same phenomenon. So it's data-driven, it is replicable by other people in other times and places, and it might be what we call empirical. We don't know why, but we see what we see. Contrast that with a hypothesis, which doesn't have the data yet, or doesn't have enough data, or we have a suspicion, or we're not confident yet that we have thoroughly explained why it is we see what we see. All right, I have a quick quiz for you, and the question is, of these four options, which one or ones are scientific hypotheses? So hypothesis A, the moon is made of green cheese. Hypothesis B, atomic nuclei are the smallest particles in nature. Hypothesis C, a magnet will pick up a copper penny. And hypothesis D, cosmic rays cannot penetrate the thickness of your textbook. So we're not asking whether or not you agree with these, we're asking which one of these is a scientific hypothesis. What is your conclusion? Well, actually, they all are scientific hypotheses. They're all testable. They are all things for which we could make experiments. They can be proven right or wrong with data. Remember, data is our friend. Here's another one. Which one is not a scientific hypothesis? Protons carry an electric charge. Or B, undetectable particles are some of nature's secrets. C, charged particles bend when in a magnetic field. Or D, all of the above. So think about it for a minute. Go ahead and pause the video if you want. Which of one of these is not a scientific hypothesis, and why? Which one is not a scientific hypothesis? Well, if you look at A and C, those are both things that are measurable. We don't know if they're right or wrong, but we certainly can take data to test that. Now B, is there any way that we can test with data whether or not something is a secret? And of course we can't. So answer B, this thing about being a secret, is not a scientific hypothesis because we can't test it. So with the scientific attitude, we've talked about theories and hypotheses. Let's look a little bit further. What's a law or a principle? Well, a law or a principle is a hypothesis that has been tested repeatedly. A variety of people in a variety of places and cannot be contradicted. We talk about the law of gravity that has been tested and argued and debated for so long that we're on to other things. A law or principle, not that we couldn't open it up again, when we learn something new, but we've probably exhausted everything we've got in front of us now to challenge that. A theory, on the other hand, um, is a little bit different than common language. We're going to try to use physics language or scientist language. A theory is well validated by a lot of data, a lot of information, but it's starting to explain the why. Our law or our principle is describing the what, and our theory is describing the why. And here's a better take on it. All right. Hey, time for another quiz. Here we go. So which one of these often changes over time with further study? Do facts change or do theories change? Do both of them change or do neither of them change? Think about it for an instant. Go ahead and pause your video right now if you want to let that digest for a minute. But which one changes over time with more study? Well, in fact, both of them can change because we learn new information, we get more data, probably because our observations change, our point of view changes, our technology changes, the level of detail by which we can observe or describe something. But the key point here is that new information can cause us to refine both our facts and our theories. Here's another one. Let's see how you do this time. So your friend hears something on the news and she says, well, that's only a theory. Is that an accurate thing for a person to say or not? Is a scientific theory a guess? Is it random? Is it something that you can discount? Is a scientific theory, does it represent a number of facts? Is a scientific theory a hypothesis of sorts? Or is it a whole lot of hypotheses and facts? What do you think? If you want to, pause the video here, and when you're ready, go on ahead. Well, in fact, when a scientist is talking about a theory, a scientific theory, it's not random and it's different than everyday language. A scientific theory is pretty well vetted. It's being used by a combination of people and situations um, with a vast amount of data behind it. And again, remember your scientific attitude that a scientist wants other people to try to replicate results or challenge the results. All right. We are on to talking about the relationship between science, art, and religion. Are they friends or are they foes? Do science and religion, do art and science, do religion and science contradict each other or do they support each other? Well, they're really apples and oranges. Um, and it's inappropriate to take one into the sphere of the other because science is what we observe and what we conclude and what we predict about the world around us. It's things that we can see and touch and taste and smell. Whereas art is a person's interpretation of the human experience and does not need to be validated with data, does not need to be reproduced. It's a person's point of view in a point in time. Religion is the systems of faith and worship. Now, can these three support each other? Absolutely. Generally, though, when the three contradict each other, it's because somebody is using something wrong. And it's not the point of view of this class to pursue this, but certainly something that you want to talk about with your friends and with some trusted adults. Art and science together gives us a whole wonderful view on our world. Putting religion with science, both answer unanswered questions. It's a way to examine and further understand what we don't know. They're friends. They work together. And again, don't be drawn into arguments where one pits one against another. All right, here's a hard question. Imagine that there are both, thankfully, a pilot on an airplane and a worship leader or a person of great faith on a commercial jet airplane. And who should perform a marriage? Now, it's a silly question, but there is a point here. Do you think that the pilot should fly and the worship leader should perform the marriage, or the other way around? Should we put the imam or rabbi or priest or pastor to fly the plane and let the pilot perform the marriage? Should we let the pilot do both, or should we let the worship leader do both? What a silly, silly question. But think about why do you answer the way you do? Well, people have different skills, they have different levels of interest, they have just different areas of expertise, and that's how our society works. So, we've talked about science, scientific measurements, math, scientific methods, the scientific attitude. We're to the point of science and technology. What is the difference? How are they the same? And how are they different? Well, science, sometimes we talk about science as being basic science or research-based. We're gathering, we're organizing knowledge. Technology is around applying it. So taking that knowledge and using it for the good of humankind. Are they related? Absolutely. Are they different? Absolutely. Okay, we're to the very end of our lecture. Why do some people call physics the basic science? Well, there are a lot of physical sciences, science about the physical world around us. We have life science about the living things around us. And one can really make a pretty good argument that they all apply the things that we study in physics, particularly classical physics that we're doing now. And if you go ahead into modern physics and theoretical physics, again, they tie very closely into the other sciences. So here's another quiz. Some people say physics is one of their hardest classes that they take. What do you think? Do you think physics is the simplest? Still the hardest? Do you think that it's kind of in between chemistry and biology for being hard? Or do you think it's only for the really smart people? This is not one you have to think about very hard. You already have an opinion on this one. What we're going to say is that physics is the simplest. You're going to have very little memorization. You're going to have very few terms and labels and categories to memorize. And the other sciences do, in fact, apply physics to explain what they are teaching.